So starting with the vestigial sideband, what it is and why do we need it. So let us recall in the amplitude modulation what we have covered so far. So say we have message signal m of t, and if we take the Fourier transform of it, so we would have the spectrum which is m of f, and considering that the message signal, it has a bandwidth of bm. So in the AM schemes we have double sideband pressed carrier, then we have double sideband with large carrier, also we call it as AM, and then we have something that we call as single sideband. In today's lecture we have vestigial sideband, VSB. This SSB and VSB, it comes in both with carrier and without carrier. So we can have and or plus C for SSB and VSB. So this can come with carrier or without carrier. So starting with the bandwidth of DSB-SC, so it has a bandwidth of 2 bm. For AM again, we have the similar structure, but now we have a carrier at carrier frequency FC, and again the bandwidth is 2 bm. So both of them, DSB-SC and DSB-LC, both of them are not very bandwidth efficient. So that is why we move towards SSB. So in SSB, we are either sending the upper sideband or the lower sideband. If this is our carrier, so we may be sending just the upper sideband, right? So in SSB, we have the bandwidth which is BM. So then question comes that why do we need VSB when we have already achieved a solution in terms of SSB, right? So the answer to that is this SSB has some limitations, and that limitations is at this point over here. We need something which we call as frequency hole, and in terms of the message signal itself, SSB is only applicable when at DC, that is at zero frequency, the power in the signal is very small, negligible. So if that is the case, then SSB is useful. But if you have significant content at DC value, so then SSB is not usable. It's not very efficient. The reason for that is if we have this kind of a structure after modulation, so at FC we have very little power. But if we have presently in this shape, if we have something like this, so a large amount of power is actually available at FC. So for that we would need actually to create this, we need an ideal band pass filter kind of a structure, which is actually not practical. The frequency selective filter that we need cannot be realized. So this is the reason that we actually move away from SSB. So that is if we have significant DC content, right? So we cannot use SSB, so we have to move towards VSB. Okay. So in terms of bandwidth, so at this moment, I would just say that if the message signal has had a bandwidth of BM, so this is our FC, this is FC plus BM, right? So VSB would be something like this. We would have some part of upper sideband, or rather complete upper sideband, and some part of lower sideband. That is, we have now a bandwidth which is more than SSB, but less than DSB-SC or LC, right? So this is approximately, depends on the filters, but usually it is around 1.25 bandwidth of the message signal. In terms of VSB model, say we have a message signal M of t. We use a local oscillator which is operating at cos 2 pi fct, and we multiply it by 2. So until here, we have just created a double sideband suppressed carrier modulator. At this point, we use a filter, and we call that filter as a vestigial filter, HV of F, and then we transmit it by means of an antenna. Right. So this is our transmitter in VSB-SC. On the receiver side, again, we would have an antenna, and we would perform the demodulation of DSB-SC initially. So that is, we are having a coherent demodulation whereby we need a local oscillator at the receiver side. So we have a mixer, and over here again we have a local oscillator, and this is cos 2 pi FCT. Again we multiply it by 2 until here at this point. It is actually just a double sideband suppressed carrier demodulation. So we can call this as S of F, and over here we would use one filter. So let us call this as H low pass filter of F, and eventually we would have output which is Y of t, and this is proportional to our message signal which is M of t. So this is basically the transmit and receive block or modulator and demodulator of VSB. So let us visualize all of this by means of spectra. So let me call this as steric 1, that is the message signal. So in steric 1, we have basically a message signal. This is our M of F, and let us say it has significant value at DC, and this is BM. At the mixer, we have basically this is nothing but two delta functions, and they are at minus FC and FC. So in time domain they are multiplying. So in the frequency domain, this would be convolving with this one. So eventually we would have this appearing at FC, and again this appearing at minus FC. So this is our steric 2. So next we have a filter which we can call as steric 3. So its spectrum is something like this. So again we have FC and minus FC, right? So we make a margin over here, and we say we have something like FC minus FV, and over here this is FC plus FV. This is FC minus BM, and this is FC plus BM. So in the DSB-SC, in the above figure or spectra, this was the upper sideband, and this is the lower sideband. Again, the upper sideband and the lower sideband. We make a transition from the lower sideband. This is our lower sideband. So we construct a filter such that we start somewhere in the lower sideband, and we go up to some point in the upper sideband, right, until this point, right? So this is FC, the center frequency, and we have this transition, right, gradual transition from FC minus FV to FC plus FV, and then we have the filter, and then it would decay down like that, right? And similarly on the left hand side we have this structure. So this is basically the construction of this filter, which is represented over here. So at this point, which is steric 4, we are basically transmitting the vestigial sideband signal. So we have at steric 4. So basically this is our VSB of F. This is the one that we are transmitting, right? So if this passes through this filter, so eventually what we would have is, until this point, after this point to this point, everything is actually one. So we would have this chain as is, so there will be no change from FC minus FV. And in between this point over here, we would be having some lower sideband and some upper sideband. We have a structure which is something like this. So in short, we are missing some information in the upper sideband, but at the same time, as compared to SSB, now we are gaining something from the lower sideband. At least some part of that is still there. And again, this would reappear over here at minus FC. This was basically phi DSB-SC of F, right? And this is our filter, which is HV of F. So if this signal passes through this filter, eventually we're getting this spectra, this plot. And this is the one that actually we are transmitting. Mind you that this is now FC, this is FC plus B, and this is something that we have referred to as FC plus FV, and this is FC minus FV. And this is referred to as steric 4 in the block diagram. Now this steric 4 is again received at the receiver side, and we again multiply it with the local oscillator. So if again we multiply it with a local oscillator, and that local oscillator is operating at cos 2 pi FCT. So we would have an impulse at FC again, and another impulse at minus FC. Right. So this is the second local oscillator at receiver. Now again, the received signal would convolve with the local oscillator. So we would have a convolution over here. So if we have a convolution, so all of this would basically move to here, and it would also move to here. Let's follow this blue curve again. So if this convolves with this one, right? So this is at minus FC, and now it would be moving towards the right side, that is plus FC. So now at 0, this would appear over here. So this FC is now at 0, and this would go to 2FC. So these two are coming from the convolution with the impulse at FC. Now the second one, again these two would convolve with the impulse at minus FC, right? If they convolve with the impulse at minus FC, so this was FC, and it would add with this FC, so it will become 0. Eventually we would have this translated to here, so we would have, right, and this would go over here, and you would have something like this is minus 2FC, this is 2FC. This plot is basically the one that we had at over here, S of F. So let us call that this is steric 5. So this plot is our steric 5, and we have also called it as S of F. But this S of F can have a simpler construction, and that simpler construction is actually such that you have at 2FC and my 2FC, like that. And around 0, now these two would add together, so you would have something like this, because this blue spectra would add with the green spectra. So if they add together at this point, this is say 1 and this is 0, and at this point this is 1 and this is 0. So linearly one is increasing, at the same time the other one is decreasing. So if you add both of them together from here until here, you would have a constant value of 1. So afterwards, this S of f over here, now this passes through this low pass filter. So this is our S of f, right? And in this S of f, you have a content at this frequency, which is low frequency, and then you have a content at high frequency. So eventually, we would use a low pass filter over here, right, to reject this part, and we would obtain this signal at the end. So this is basically the demodulated signal at this point over here. So these two filters are very significant in this modulation scheme. So by understanding these two, basically we cover this area of amplitude modulation.
The vestigial filter and the low pass filter are related with each other. So let us see the construction of these filters.
So let us try to understand this mathematically, what is happening, right? So the steric 2, which is double sideband stressed carrier. So if we look into this, this is nothing but m of f plus fc plus m of f minus fc, right? So basically this is appearing over here and this is appearing over here. So next we have this filter. So this filter is HV of f, vestigial filter. And after that we have this spectrum, which is phi VSB of f, right? So this phi VSB of f, so this is simply the multiplication of these two, m of f plus fc plus m of f minus fc, and then we are multiplying with the filter, that is hv of f. So if we multiply these two together, so we are getting eventually this signal, and over here this signal. So next, this is now convolved with this one, with two delta functions again, one at fc and another one with at minus fc. So this is something that we call as S of f. So this is simply phi VSB f minus fc plus phi VSB f plus fc. So this convolved at minus fc, so sorry, plus fc, so you got this, and then again this convolved at minus fc, you are going to get phi VSB of f plus fc. So this is our S of f. So let us expand this phi VSB f minus fc. Note that this is our phi VSB of f. So if we expand this phi VSB of f minus fc, so we have a minus fc over here, and then we have a plus fc over here. So we would have m of f plus again over here, and this fc. So we would have m of f minus 2 fc, right? So this minus fc would cancel this minus fc, and this minus fc would add with this minus fc. So you have minus 2f minus 2fc and m of f, right? And at the same time, you have this filtered at the end. So this is hv of f
Minus fc.
plus. Now you are having the second part, which is f plus fc. Now if this plus fc, if this adds with this plus fc, so you would have m of f plus 2fc plus again this fc, and this fc would cancel off and you would have m of f times h v of transitioned to this place. So that is f plus fc. This means this would be f minus fc. Let us again simplify this second equality over here. So we are going to combine the mf terms, right? So if we combine the mf terms, we would have hv of f minus fc from here and hv of f plus fc from here, and both of them have the common element of m of f plus the remaining term, that is m of f plus 2fc, and this is with hv of f plus fc plus this part over here, m of f minus 2fc, and then this part with it, that is hv of f minus fc. So this is basically something that is appearing over here. Okay, this is available over here, right? And finally this part is over here. So if we use an appropriate low pass filter, so from the third equality we're going to use a low pass filter, and this is referred to over here in the block diagram as well, that we're using this low pass filter. So by means of low pass filter, this is cancelled, that means this is cancelled, again this is cancelled, so this means that this is cancelled, and eventually you're having this appearing in terms of a filter which is having a shape in terms of message signal, right? So we are having an output y of f that is equivalent to this characteristic of a filter, which is hv of f minus fc plus hv of f plus fc times m of f, right? And the rest of the terms are basically cancelled off. We understand that the low pass filter is basically having a relationship with this expression, specifically with this part. Initially we had m of t or m of f at the transmit side, and after doing all the processing at the receiver side, again we are interested in m of f, right? So we need to cancel out this aspect. So we are having a filter which we call as low pass filter of f. So this is basically the reciprocal of this expression, that is we have hv of f minus fc plus hv of f plus fc. So hv of f is this filter hv of f, and the low pass filter hlp of the low pass filter of f, this is basically linked with the vestigial filter at the transmit side by means of this expression. So let us take one example just to understand what is going on in here. So say we have a message signal m of f, right? And this message signal has a bandwidth of 6 kilohertz. Okay. And then we have a filter which is a vestigial filter, and we call it as H vestigial filter of f. It has a carrier frequency FC which is at 20 kilohertz, and it has a transition from 18 to 22, and then it has a value until 26, right? So it has this kind of a characteristic. The filter has this kind of characteristic. So this is basically 1 and this is 0.5, right? So this is our filter. The question is, we need to design a low pass filter such that we achieve a distortionless reception. So we have to again go back to this expression which defines that how the transmitter filter relates with the low pass filter at the receiver side. So basically we are interested in HV of F minus FC and HV of F plus FC, right? So if this is our HV of F, what would be HV of F minus FC?
Frequency shifting, that is,
This means that this would go over here.
carrier frequency at minus 20 would now be at 0.
This minus 18 is now plus 2 and minus 22 is
Minus 2.
so this is the one that we get. So this is minus 6. Okay. And this would move towards 2FC. This means that we have now something at minus plus 40. So we have this structure, and at the same time our HV of F plus FC. Now all of this would be moving towards plus FC over here. That means this is now shifted towards the center 0, right? So we have, and this would go to minus 2FC. So if we add these two together, that is HV of F minus FC plus HV of F plus FC, right? Adding these two together, note that this is 0. So in this 0, this was minus 2 and this is 2. So between minus 2 and 2, the value is basically increasing. And then we have this function. How much is it increasing? This is basically increasing by 0.5, right? So this is from 0, it is increasing to plus 0.5, and it had a value of 0.5, and it is basically decreasing to minus to 0, from minus 2 to plus 2. So now if we add these two together, we would have a shape which is at 0, from minus 2 to 2. It has a consistent value of 0.5, and after that over here we have a value of 1 at 2 until 6. We have a value of 1, and then on the left side of the spectra until minus 6 we have a value of 1 again, and then it will drop down. So this is our HV of F minus FC. But note that our low pass filter is basically the reciprocal of it. We have to take the inverse of this. So we have around from minus 2 to 2, we have a filter which has an amplitude of or amplification of 2, from minus 2 to 2 kilohertz. in frequency, right? And from -2 until -6, basically it is simply 1. So this is basically the low pass filter. Basically, if this is going upward, it doesn't matter because it is because there is no message there. So if there is no message there, eventually it will become 0, right? Or there is no content in that spectra. So we have to make sure until here that our filter is working.
Note that
Your filter which you have used at the transmit side, which is this filter, right? So this HV of F, this is actually following a characteristic, and that characteristic is that if this is our carrier frequency FC and this is FC minus FV, FC plus FV.
we have the spectra of this shape on the transmit side.
So from here to here, right? So we have an even symmetry and we have a consistent slope, right? So we may have a different slope, but the symmetry has to be there. Maybe like this. But this and this are, if this is, if you consider this as a reference, so this is basically an anti-symmetric kind of a behavior, or rather an odd function kind of a behavior. So this behavior is actually very important in the construction of VSB filter. So if this is not there, then the amount of upper sideband and lower sideband, they are eventually added up. Where they are added up, they are added up over here at this point. So they would basically not be adding up constructively, and you may lose some information. Okay. So this filter is applicable for say frequencies which are less than or equal to bandwidth of the message signal. In terms of bandwidth, how these 3 or 4 different schemes relate with each other. So the largest is actually double sideband suppressed carrier, and this is consuming 2 times the bandwidth of message signal. And this is actually equivalent to double sideband large carrier, or simply AM. And again, this is consuming 2 times the bandwidth of message signal. So this consumption is more than VSB, which is approximately consuming 1.25 bandwidth. This is actually using more bandwidth than SSB, which is utilizing 1B, right? So in terms of bandwidth, VSB is stationed over here. So again, VSB and SSB, you can transmit them with carrier or without carrier. So considering them, we are transmitting them with carrier, right? We're transmitting carrier with VSB and SSB. So in that case, how does the efficiency actually relates with the power efficiency relates with all of these schemes? That is the power efficiency. So in our previous discussion, we had mentioned that the power efficiency, the maximum power efficiency for AM or large carrier is basically 33%, right? That is, you have a carrier at FC, and then you have the upper sideband and lower sideband. 66% of the power is basically consumed in the carrier itself, the reference signal. So when it comes to SSB, now we have one large carrier and then we have just one upper sideband, right? So in this case, the power efficiency now reduces to roughly around 17%, right? So this is that. And if we link it with VSB, now we have a carrier at FC, but we have some chunk of lower sideband and major chunk upper sideband, right? So this is in between the single sideband and double sideband. So approximately you can say we would be consuming something like 20 to 21% of the power in the sidebands, and remaining power will be used in transmitting the carrier signal. In terms of applications, where do we use this VSB? So let us consider an analog TV, that is terrestrial signal of television. So in this TV signal, basically we are using two schemes. So let us again visualize the spectra, and we have a video signal, and then we have an audio signal. So say this is the carrier frequency of our audio signal. This audio signal is, we use frequency modulation to transmit it because FM is more robust in terms of channel nonlinearities, and noise has little effect on FM. So we use this spectrum of the available spectrum for the TV signal. Then comes the video signal. So say this is the carrier frequency of the video signal. But video signal has significant DC content. So that means we cannot use SSB. And it would be unwise to use DSB or AM for that, right? So it would consume a lot of bandwidth. So we use VSB. So that VSB is, we take a very small portion of the lower sideband, and then we miss some information from the upper sideband. But anyways, we use this bandwidth for the video signal. So overall, end to end, we are consuming 6 megahertz of bandwidth, and within that, roughly around 0.5 megahertz of bandwidth is used for the audio signal, and this around 1.25 megahertz of bandwidth. This is basically from the VSB that we are considering lower sideband. And it does not contain information, but this is required in terms of transmission, right? So this is our overall spectrum of the TV signal, and on the negative frequencies we would have the same spectra as well.